All right, so I did send out an email that had a summary of the grades, but that was way back on Thursday night, like at midnight or something, so I don't remember any of it, but I think the class average was around a 70, right? Okay. There was a group of students I was a little concerned about, and then there were quite a few A's, I believe, right? 9 A's. So that's the first exam. Remember, it's only 15% of your grade, so that can be a good thing or a bad thing, you know. I talked about this before. If you did really well on this exam, good, but it's only 15% of your grade, so you know, you don't want to take the foot off the gas yet. If you didn't do as well as you had wanted to, then it's not the end of the world, because again, it's only 15%, but you know, you have some work to do, all right? Oh, gosh, I don't know. It's on the calendar. A long way from now. April 15th. The day before exam 3. Or the Friday before the exam 3. Yeah. So, okay, we do have a little bit of administrative stuff to take care of. I have an appointment on Monday that I cannot get out of. That's at 10 a.m. And I don't think there's any possible way that I can be here for class on Thursday. All right, did I say Wednesday? Thursday. This Thursday, okay? The next time we meet. So we have two options. One option is we get a sub in here and they go over and they cover the material we're supposed to cover, right? Okay. Here we go. Where are we? There we go. Okay, so we either have a sub, which I wouldn't even be able to choose who that is. It would just be whoever could do it. And then the other option is that we just don't have technically class that we meet here. But what I do is I require you to watch last semester's lecture over what I would have lectured over. Those are our two options. So that's good, both of them?
No.
So
We'll watch him here with the stuff.
Yeah, it's a good idea. So just a quick show of hands. How many of you are in favor of a sub? Yeah? Sub? Okay. It's all right. I mean, don't feel bad. All right. You like subs? Okay. And then how many of you are okay with doing the video online? Is that okay? A U sub? We can do a U sub. Okay, so now here's what I'm going to do. I'm going to hold you to watching that video because it's important that you actually do get exposed to the material. So what I've already done is I've found the video on YouTube that I'm going to use. I just need to figure out where we end today so I know where to pick up, and I will send you an email. It'll have a link. It'll take you right to the actual second in the video where you should start. All right? And then I'll tell you how much of it to watch. All right, I think it'll be about an hour. I don't think it'll be the full hour, 40 minutes, but it's better than nothing, which is what would happen if I cancel class. And with a sub, you just never know. Anytime you ever have a sub, you come back in, you wind up kind of going through it anyway, again. So, okay, but let's see. If for some reason that appointment gets canceled today, then I'll let y'all know. But look for an email officially from me later today saying that, you know, here's your assignment, no class on Thursday, all right? This Thursday. All right? Okay, so with that said, if you have any questions over how I graded or any questions over, you know, anything on the test, then please, you know, get in contact with me, get in touch with me. Let's sit down, go over the material. I'm not going to post the key online, so I'll let you go figure out, you know, what mistakes you made. And I did say in the email that I did not grade number 10. I counted it as a bonus, right? And then you had the bonus, which was bonus. Now, each one of those, number 10 and the bonus, could have been 5 points each. So if you got 10 right, then you got an extra 5 points. Some of you, it says plus 10 on there. That was before I had decided to drop, and it changed after a little while. So I said, no, it's plus 5. So
the bonus is worth 5 points?
bonus was worth 5 if you got it right, and number 10 was worth 5 if you got it right. But if you got the bonus right, it'll say like plus 5 on it.
Oh, mine's plus 3.
Oh, that means it's almost right. Yeah. Was it plus C? No, you sure? I don't know.
That's what 2 points.
It was a bonus. Bonuses have to be right. They have to be perfect. Okay, let's get down to today's. Anybody need a copy of the notes from last time? You need a copy? I only have a few here. Oh, that's a different one. Anyone else? I only have 2 more copies. Well, I need 1 copy, so y'all have to share. Did I pass these out last time?
Yeah.
Y'all don't have them? Do we have more than 1 at this table now? Y'all are sharing. Yeah.
I just want to know.
Hold on. It's not this one.
Oh, no?
Oh, wait. Yeah, it is this one. Yeah. Oh, you wanted an extra one? That's it. Y'all will have to share it. Yeah, that's the one I'm talking about. Sorry. Okay, and then the next thing is the notes online. I thought I was going to project them, but do y'all want me to project the notes? Yes? We're going to get a late start here today. So what did y'all think of the exam? I mean, did you think it was reasonable?
Yeah.
Reasonable? Easy. Okay.
Stop it.
I was talking to one of your classmates, and one of the things I think I want to keep track of on the next exam is how much time it takes you to finish the test. Because there were some students that finished that test with half an hour to spare. And I'm at least going to keep track of it. And I guess what I'm thinking is that a student who can finish the exam in 30 minutes versus a student who can finish the exam in the full 140, if they both do the exact same work, are they the same student, so to speak? You know what I'm saying?
No.
No?
Like a bonus for
You don't like that? Kind of like a bonus for being quick.
Well, Professor, if you're smart, you're gonna spend the whole time taking all the derivatives of all the integrals you did. I mean, because I finished that exam.
Like I said, I don't know how I would do it. I'm going to keep track of it. Okay? Because you're right. There are people who are going to want to go back and double check everything, and you don't want to get penalized for that. But I just at least want to see, like, if there's a trend. The people with the A's, are they finishing early? Just that sort of thing. So next test, if I ask you when you turn it in to like write down the time, that's what I'm kind of getting at. I want to be able to kind of look at it all again and say, okay, look at this group. They all finished early. This one didn't. So.
Isn't that only going to apply to somebody who makes a generally B and up? Because if they get like less than a B, they probably just didn't do something.
But like I said, look, I don't know. I've never kept track of time. It's just something I'm thinking of looking at. Okay, we finished up last time. And now we're 6.2.3, and now we're going to do 6.2.4. So we're going to do trig integrals. So we're doing integration that we have trigonometric functions within the integrands. And there are a few that we already know. Hopefully we all know that the antiderivative of secant squared x is tangent x plus c. And the antiderivative of secant x tangent x is secant x plus c, right? So those are just from Cal 1. Also, we learned this little thing about if we had a linear expression inside, that we have to scale out by that, right? 1 over a. Good, yes? Okay, so that's nothing new. And then we want to have some sort of strategy, which is on your sheet here, as to how to attack integrals that have secant and tangent combined in them. Alexis, here you go. I think the grade's on the back page. So there's a set of strategies. It's going to be very similar to what we did with sine and cosine. Remember how we would look for like cosine squared and rewrite it as 1 minus sine squared, or if we had sine squared, we'd write it as 1 minus cosine squared. Same sort of thing, but we're going to use some different identities. Remember the identities, right? What are the identities that we have? Tangent squared x plus 1 equals secant squared x. Right? That identity from pre-cal. And we can rearrange this identity. We could solve for tangent squared x. It'd be secant squared x minus 1. Right? So we have to keep those in mind today as we're moving through and making substitutions. All right, so I'm not going to read through the steps, the procedures. Let's just get to an example, and then we'll go back to the steps. So our first example here is to find the antiderivative of tangent to the 4th power of x times secant to the 4th power of x dx. All right, so refer to your sheet. And on the right-hand side, how to integrate powers of tangent and secant. If the power of secant is even, well, we've got that first case, right? The power of secant is even. It says, save a factor of secant squared x, and then use this identity, the one right here, that's solved for secant squared, right? So what do they mean by save a factor? Just like break this secant to the 4th to secant squared times secant squared. So I'm going to rewrite this integral as tangent to the 4th x secant squared x times secant squared x dx. And then rewrite the secant squared as 1 plus tangent squared, right? Or tangent squared x plus 1. So if I do that, I'm going to tangent to the 4th x. Why am I putting parentheses? It's going to create two terms, right? So I need parentheses because that tangent to the 4th would have to distribute through. So secant squared x becomes tangent squared x plus 1. Right, that's this. And then continue on. What does it say I'm supposed to make a substitution of? U is tangent, right? And the reason is because the derivative of tangent is what? Secant squared. So this is kind of like a basic substitution now. If you let u be tangent, right, the derivative of it's right here, secant squared. So that's going to be our substitution. So I let u now be tangent x. du is secant squared x dx. And then I'm going to rewrite the whole integral in terms of u. So u to the 4th, I hear you over there, u to the 4th times u squared plus 1, and then this is all du. And how are we going to integrate this? Distribute and then power rule, right? So distribute, before we integrate, distribute. U to the 6th plus u to the 4th du. And then the antiderivative of that is 1/7 u to the 7th plus 1/5 u to the 5th plus c. And then go back, replace u. What's u? Tangent. So this is going to become 1/7 tangent x to the 7th power, right? So I'm just going to put the 7 here. And then plus 1/5 tangent x to the 5th power, so put the 5 there, and then plus c. That's it right there. That make sense? Any questions? Sure? Okay. Pretty straightforward? Okay. All right, let's look at the next example. The next example, we have tangent to the 5th, secant cubed x dx. Keep in mind, though, that these things that are on this sheet here, these are strategies, okay? It's not cookie cutter works every single time. Sometimes your integral, even though you try this, won't work out. All right, just keep that in mind. If this were like a universal, always do it this way, then we would tell you that strategy is something else. It's something that you bring out, you try it, and if it fails, it fails. Try something else. All right, so here, the difference here is we don't have an even power of secant, do we? So what does the second strategy say? If the power of tangent is odd, save a factor of secant tangent. So that means if this is odd, I'm going to peel off one tangent, and I'm going to peel off one secant. And I'm going to rewrite it like this. Integral would be tangent to the 4th x, right? Secant squared x. And I peeled one tangent off and one secant, right? So I'm going to write secant x tangent x. Why do you think I am peeling off this secant x tangent x over here? Close. This is the derivative of what? Secant, right? The derivative of secant x is secant x tangent x. So if I can get all of these written as secants, then my u could be secant, and there's its derivative. And this will be another basic substitution. Do you all see that? But can you get these to be secants? Well, this is already a secant, so there's no problem there. Can you convert the tangent to a secant? Yes, we can use the Pythagorean identity that we just had up on the board again. We know that tangent squared x, we said was secant squared x minus 1, didn't we? But this is tangent to the 4th, right? So it's that squared. So let me rewrite this. This is going to be integral. I'm going to write secant x, secant squared x minus 1. That's tangent squared, right? But since it's to the 4th, squared. And then secant squared x, then secant x tangent x dx. Questions? So the substitution we make now is u is secant x. Are you liking this more than that integration by parts and stuff? Seems a lot cleaner. All right, so u is going to be secant x. The derivative of it is secant x tangent x dx, which is what we have right here. So now it's just a matter of rewriting everything. So this integral becomes, in terms of u, what? U squared minus 1. That quantity squared. And then u squared again, du. Y'all with me? And then how would you like to do that? Yeah, just expand that out, right? Can everyone square that? Yeah? So let's square that. This will give you u to the 4th minus 2u squared plus 1. That's what happens if you square that. You still have a u squared on the outside of it, du. Now just distribute the u squared through, and you're going to have just power rule, aren't you, at this point? u to the 6th minus 2u to the 4th plus u squared du. And now just power rule on each one, and you're in business. So what's the antiderivative here? 1/7 u to the 7th, right? But u is secant. So secant x to the 7th, right? And then minus 2/5 secant dx. Secant of x to the 5th power, right? And then this last one plus 1/3 secant cubed. Yep. Very good. Okay. We all right? All right. So it looks like we can handle a lot of trig stuff now. Trig, integrals that have trig functions in them. These are at least two strategies that we can employ. All right. There are some other cases that aren't as obvious. So looking at the antiderivative of tangent, this is a formula. Isn't there a formula on your formula sheet for this? Yeah. There is, right? But let's try and get it without the formula sheet. So if you were to go off of this, you would have tangent as odd, right? And it says peel off a factor and have a tangent secant, right? But you don't even have a secant in there. You can't, it's not squared. You can't do anything with that, right? You don't see what I'm saying? Mm-hmm. All right, so to do this one, we just got to remember to go back to the basics here. Let's go back. Whenever you have trouble with an integral with trig stuff in it, get it in terms of sine and cosine. That's usually the kind of workaround. If you're hung up on it, try and get everything in terms of sine and cosine and see if that makes it any better. So when you look at that, how would you do that? U is cosine? This is a basic sub, right? Just do a basic sub. U is cosine. What's derivative of cosine? Sine. It's up there, right? You don't want to go the other way around, though. You don't want to let u be sine because the derivative is cosine. It's down there, right? So you want the derivative that's going to be up top, not on the bottom. So I said the derivative of cosine is sine. It's negative sine, right? We all know that. So du is negative sine x dx, which is exactly what you have here, right? Well, almost. You're off by a sign, aren't you? Negative. So negative du is sine x dx. So if I were to rewrite this integral, the sine x dx is going to be replaced with what? Negative du. And then the other part is 1 over cosine, which is just 1 over u. So the negative du, I'm going to write like that, negative du. Then I'm left with 1 over cosine x, which is u. And the antiderivative of 1 over u is natural log u. So I'm going to have negative natural log absolute value of u plus c. And then what's u? Cosine. Which negative natural log absolute value cosine x plus c, which does not match the formula in the back of the book. Formula in the back of the book, or the formula sheets that you're allowed to bring to class, those things, it has what? Natural log secant x. So how are they getting that? 1 over cosine is secant, so how are we going to make that 1 over cosine? You have properties of logs. Remember properties of logs, right? No. So if you have n times natural log x, that's the same as natural log of x to the n. So if you have powers up here, remember you can bring them out? Well, if you have a number out here, you can bring it up. So this negative 1, this is negative 1 right here, right? If you bring that negative 1 up, it becomes cosine x raised to the negative 1, not the inverse trig function. it's raised to the negative 1, which means 1 over cosine, which means secant. So this is the same as natural log absolute value, secant x plus c. So we had it, it just looks a little different than the book.
It's still negative, right?
No, the negative one came up and we used it to do the reciprocal. All right, let's look at b, the integral secant x dx. This is a very, very difficult integral, all right? And I wouldn't ask you to get this on your own. I would just tell you, let's look at the formula in the back of the book, all right? That's what I would tell you, because there's really not a method that we have that is going to actually get this, all right? Right now, integration by parts isn't going to work. This little cheat thing is not going to work. Rewriting it as 1 over cosine is not going to work. There's nothing that we have that's going to work on this. And the book talks about this. The book talks about the proper way to go about this one. Okay? And it was basically, who has their book readily? Mine? Thank you. It's on, yeah. I'll just show you right here. Here's what you have to do to make this problem work. See, I don't even remember what the step is because it's so crazy random. You're just going to multiply that secant x by 1. But that's the one you're going to use. And if you do that, good things happen. All right? Do we want to see? I mean, I think right now we'll just kind of wave our hands at this and we'll say, like this part right here, like how in the heck did someone know to do that, right? But let's just say that we did this. Let's see what happens. On the top, what do we get here? Let's distribute the secant through. Secant squared x plus secant x tangent x, right? Over secant x plus tangent x dx. Agreed? See if you can follow what they do in here. I wonder if they show you all the steps. Yeah, no, they don't show you all the steps either. So make a substitution now. U is secant x tangent x plus tangent x. What is the derivative of that? Secant x tangent x, that's the derivative of secant x, plus what's the derivative of tangent x? Secant squared x. Anyone see that anywhere? That's the numerator. So if you let the denominator be u, the numerator is the derivative. It works, right? I mean, it works, but like where would you come up with this and how would you see that? That's a different question. So this is what happens in mathematics a lot of times, is you get a problem that everyone's hung up on and all these people attack it, and then eventually someone gets it. And they do something that seems unnatural and it works. But it's persistence that gets someone to that point, right? That's persistence. Why would you try that? I don't know, because it works. All right, so all you need to know, let's rewrite the integral. What would this turn into? The top is du, isn't it? The bottom is u, so just 1 over u du. Antiderivative of that, natural log u. What was u? Secant x plus tangent x. So if you go back and look in the back of the book, the antiderivative of secant x is the natural log of secant x plus tangent x plus c. So, yeah, you wouldn't be asked that. I just wanted to show you, like, hidden, here's a 1, and wow, okay. So we are still humble. We can't do all integrals, all right? We never will be able to. All right, but let's look at secant cubed. What about secant cubed x dx? So you look at the cheat sheet here, and you got, is the power of secant even? No. Is the power of tangent odd? I don't see a tangent. Split it up how? like factor a secant and make it secant squared x secant x? Like that? And then what?
And then you secant squared and then use the 1 plus tangent squared.
This could be turned into 1 plus tangent squared. But then what would if you're going to let u be tangent, what's the derivative of tangent? Secant squared, but you only have secant. Do you see what I'm saying? Let me write it down over here. I'm not going to go this route, okay? But I think that's the suggestion right now. See, right now if you say, okay, let's let u be tangent, this will be 1 plus u squared, but then this is not du, is it? So your other hope is maybe to get a secant tangent out here. But you can't get a secant tangent out here because how are you going to get a tangent out of this? How do you get a tangent? You can't factor a tangent out of this, can you? They don't both have tangent? So we're kind of stuck.
Can you use identities again? In the same problem?
What's that? Yes, integration by parts. Okay, yes, I think I like that. So this splitting off of this splitting though, let's split it and then do integration by parts. Okay, since you suggested it, what do you want to do u and what do you want to do for dv? Secant squared? Okay, and then that means this one has to be secant x, right? dx? What do y'all think about that?
Flip it. No.
Do it the other way?
Yeah.
Or do it this way?
We can take the integral from
We can't integrate this, can't we? It'll become what? Natural log of secant x plus tangent x. And down here, derivative will be 2 secant x times secant x times tangent x. And then we have to do the integral of these two. Ooh. Maybe the other way? Maybe the other way. Yeah, let's try it the other way. How about just secant here and secant squared here? Yes, good. You see the difference? Okay, so let's see. The derivative of secant x du would be secant x tangent x dx. And then the antiderivative of secant x is just tangent x. That good? When you do this, I hope we're able to handle it. We'll see. Okay, you ready? The integral secant cubed x dx, which was our original integral, right? Is equal to ultraviolet minus voodoo. Ultraviolet secant x tangent x minus integral voodoo. When you multiply these two, you get tan squared times secant. Tan squared x times secant x dx. Are we all good with that? Does this fall into one of these formulas?
Yes, number
2 if tan is odd? No, tan's even. If we do integration by parts again, what are you going to choose as your u and dv? You don't want to go and reverse what you just did. How about this? How about this? See if you agree with this. I'm going to rewrite this again. I'm going to keep the original integral here. And this is going to be secant x tangent x minus integral secant squared x minus 1 times secant x dx. Anybody see it?
Yeah.
What do you see?
The substitution, the identity from tangent squared x, right?
Yeah, that's what I did. Tangent squared is this. But what's going to happen here? I'm going to distribute the secant through and get what? Secant cubed, and then secant, right? It'll be minus integral secant cubed plus integral secant, right? Integral secant cubed is over here. and over here. Didn't we do something like that before? Okay, so watch.
It's separated into two integrals, right?
Yes, I'm going to split into two integrals before I do that. So I'll have minus the integral secant cubed x dx plus the integral secant x dx. So minus this times this is secant cubed x, and then minus. And then this times this is negative secant x, minus minus is plus, yes? Now, do y'all see it? Is that more clear now? Do you see it? I have negative one of these over here, and I have one of them over here, right? So I'm going to add one of them to both sides. Yeah? And then can you find the antiderivative of secant by itself?
Yes.
Yes. We just did that. Well, someone else did it and we saw it, right? Okay, so how many integrals do we have on the left side now? Two of these? And then the only thing left over here is what? The antiderivative of this, which we said was plus natural log secant x plus tangent x. Yes, divide everything up by 2 and plus c, yes. Any questions? Go ahead.
No, I was just seeing. No, I was talking about the following, but it's minus.
Yeah, minus, yeah. See, we needed this one to be minus, right? Because if this would have been plus, then you would have subtracted on both sides and it would have gone away and it would have been useless. Okay, so divide everything by 2. So there's a 1/2 in front of that, right? And a 1/2 in front of that. And the 2 over here is gone. And the plus c, I can just leave it. So there you go. Is that formula on your formula sheets? Secant cubed? I could have sworn it was on there. Secant cubed? No? Okay. All right. We're done with that. That's the first half of 6.2. So I'm going to read this to you because I think this is important. After we master the above concepts, okay, so assuming we know now how to deal with trig integrals, we can use that idea along with an interesting type of substitution to find the antiderivatives of some rather complex functions. So the key here is that we must understand what we just did in order to do what we're about to do. These new types of substitutions that we're about to make are called trigonometric substitutions, or trig sub. So we have u substitution, right, which was our basic u substitution, right? We call it u sub. Now we have this thing called trigonometric substitution, which is trig sub. And it's very weird when you first see it. You're like, what? What are we doing? So I think what I'll do is I'll start, man, there's so many different ways to approach this. I think I'll go through like I do in the notes. Let me just show you what the general idea is here. Let's say that we have somewhere in our integrand an expression that looks like this. Okay? So you have an integral, and it's got a bunch of crap in it, whatever, and then somewhere in there you've got square root of a squared minus x squared. Let's say that we have that, all right? Where a is just a constant and x is the variable. So some example of this would be like square root of 9 minus x squared, square root of 4 minus x squared, square root of 2 minus x squared, right? All of these would fall into this format? Yes? In this first one, what would the a be? 3. Here, the a? 2. 2, here the a? Root 2. Right? A is always just the square root of that number. The principal root, so just the positive of that. Square root, right? So, y'all with me? A here? 1, right? Just 1? Okay. So let's say we have an integral, right, that has that in there. And it's rather complicated looking, and we can't figure out how to do it. None of the methods we have work. So I just decide to come in here and make a substitution in the problem. I'm going to let x, okay, see this x? I'm going to let x be equal to whatever this a is times sine theta. What? Now that's the trigonometric substitution. That is the thing that's new. Is that it does not seem like you would want to take an expression that has just little, just little x in there and replace x with something more complicated than x, right? Do y'all see that? We're replacing the variable x with this weird trig expression. But what we're doing is we're converting the problem from the variable x over to the variable theta. And believe it or not, things are going to get better for us when we do this. So let's see why it gets better. First of all, what's x squared going to be? X squared is a squared sine squared theta, right? That's what that is. Okay. Next thing, what's a squared minus x squared? Well, a squared minus x squared would just be a squared minus a squared sine squared theta, right? If I take a squared and subtract x squared, then I'm taking a squared and I'm subtracting x squared. There's x squared right there, right? But what is that? What can you do with this? What do y'all see here in common? You can factor out a squared. And if you factor out a squared, what are you left with? 1 minus sine squared. And what's 1 minus sine squared? Cosine squared, isn't it? So this just turns into a squared cosine squared theta. Now why is that a good thing? Because what are we going to do over here? We're going to take the square root of it, right? So now finally come back over here and tell me what is the square root of a squared minus x squared. What is that equal to if you make this change, this substitution? It's going to be that thing square root, right? So what is the square root of a squared cosine squared theta going to be? A cosine theta. Now I don't know about you, but this seems like a rather complicated expression. If we make this substitution, it's just cosine theta. Can you integrate cosine theta? Mm-hmm. Absolutely. So this particular trigonometric substitution is supposed to make the problem easier. All right? Understand? Now we're going to have to work through an example for you to see this, in action. So I believe my first example here is that particular case right there. So we're going to do that. So here's the integral. X cubed square root 16 minus x squared dx. Now this came up on the test. I know it was brought up by Matt, right? You brought up the different ways to do the integral, right?
Oh, yeah.
Yeah?
On your previous
On the last exam, right? What was it? Wasn't it this one?
Yeah, I thought it was the previous exam.
Okay.
And like where we had that inverse sign.
Okay. Either way, look.
Oh, the text I sent.
Yeah, the text.
Okay,
Yeah. Okay. All right. All right. So look, anytime you have an integral, there might be more than one way to do the problem. Like you could use integration by parts and do it correctly and get the correct answer. You could do a different U substitution that just happens to work, and you get the two answers. You look at them; they may not even look the same. That's what you had. They didn't even look the same, but they are the same answer. So what I'm getting at is there's multiple ways to attack integrals and still get the same answer. Do it correctly. This integral, you might be able to get this with integration by parts. There might be some quick U substitution that works. I don't think so, though. I don't think it does. We can try something. If y'all want, let's try something that we know how to do, all right? And let's just see if it works.
Separate x cubed,
Okay, you want to separate x cubed to be what?
x squared, and x.
Good. Glad you see that. And I think you're doing that.
And then all underneath that would be all u.
Okay, so you're going to let u be the entire 16 minus x squared, because then the derivative of that is negative 2x, which you have right here, kind of, right? So du, then you can solve for x squared over. So let's see how this goes. Negative 2x dx, negative 1/2 du equals x dx. So if you're sitting there watching this right now going, man, I have no idea what's going on, like that's the part of the class that I think you're kind of in trouble, okay? Because you got to be able to see this, because this is already in the past now, all right? This is stuff we've done. So I'm going to rewrite this integral. X squared is
X squared times u. Oh, it's u minus 16.
uh,
So
Negative u plus 16.
there you go. Negative u plus
16 minus u, or negative u plus 16. And then what's x? 1/2 du, right? I'm just replacing it right away, right? A negative 1/2 du, yes? And then the root of this is going to be root u to the 1/2, right? That's just written out exactly in the order. Here, here, here. I need to rearrange it. Could you handle that integral?
Yes.
I think so. I think you could do that. You could turn this into u to the 1/2, distribute it through, and we get to the answer, okay? Yeah? Okay. So we could do it this way, but I'm not going to. I want to show you this method, because if I tweak this integral just a little bit, your method is going to fail. And the method I'm showing you right now won't. All right? So this is just another tool in the toolbox, all right, for us to be able to use. With me?
Are some of these new methods going to be like replacing old ones, basically?
Not really replacing. They're actually more powerful.
Because then you could use them in like a broader.
That's right. You can use them and it's more applicable to more types of integrals. All right, so here's what we're going to do. We're going to go back to this, and we're going to say, all right, I'm stuck, or my other methods don't seem to want to work real well. But I see this right here. This looks like square root of a squared minus x squared. And I remember my teacher telling me that we're going to do something called trig substitution on something like this, right? And I needed to be able to recognize what a is. So I need to know what a is. So what's a for us here? A is going to be 4. And what is the substitution that I'm going to make? X is, do you remember what the substitution was? A sine theta. So I'm going to write x is equal to 4 sine theta. Okay? All right, so everything I've done up to here, like this, was just me looking at it, recognizing I'm going to do a trig substitution, figuring out what the A was, and then making the substitution. This is the actual where the work begins, okay? Now what I'd like for you to do, all right, is what we did in the past when we did substitutions. We'd say like u is equal to this, then we'd take derivative on both sides. Go ahead and take derivative on both sides. So dx on the left is going to be the derivative of 4 sine theta, which is 4 cosine theta, d theta. Look, theta is just a variable, right? We good with that? I'm going to replace x with 4 sine theta. I'm going to replace dx with 4 cosine theta d theta, and I'm going to replace x cubed with 4 sine theta cubed. That's what I'm going to do. All right? I'm on the fence here of how I want to do this. Look at the formulas. Look at your formula sheet, right? Well, it doesn't show you here, so you know what? Yeah, this is good. This formula sheet doesn't cheat for you. The whole point of doing this, right, was because I told you that this expression is going to get nicer, right? We can either go ahead and plug in 4 sine theta right here and plug everything else in and work it all out, Or I can do the on the side, I can look at that by itself and figure it out and simplify it and then plug it in there. What would y'all prefer I do? Do this on the side, simplify, or do it in here and just work everything together?
Put it in there.
Both? Well, I don't want to confuse you, make you do more work than you have to. What do you think you want to see?
Do the harder one.
Well,
Or like both figures.
it's the same. It's just, do you want it separated? Do you want this idea separated from that, or do you want it all together? All together? All right, let's do it all together. All right, so integral x cubed. 4 sine theta, I'm just going to throw it all in parentheses cubed. Okay, square root of, I'm going to make a big square root here, 16 minus 4 sine theta squared. Do you mind if I go ahead and square that now? 16 sine squared theta. Is that okay that that's x squared in there? And then on the outside, do not forget this, dx, which is 4 cosine theta. What? Do not forget what? Dx. Do not forget dx. So many people always, they'll forget the dx. They'll do everything else right. They forget the dx. Everything after that's, done at that point. Okay, so dx is going to be out here times 4 cosine theta d theta. So let's see how quickly you can resolve that radical, that square root. Let's see how quick you can do that. What can you factor out of both of these? 16. And that 16 will come out as a 4 out of the root, won't it? So we'll have integral 4. Okay, I'll pull that 4 out right there. There it is. Can I go ahead and cube this? 4 cubed. What's 4 cubed? 64. And I had a 4 already. Sine cubed is sine cubed theta, right? So I'm cubing both of those. This square root, we pulled the 16 out, which then popped out as a 4. What was left under here? 1 minus sine squared theta, which is?
1 minus
Cosine squared theta, right? And the square root of that is? Cosine theta. So this right here is going to turn into cosine theta. I don't like the way we're doing this. That's why I like to do it on the side. I'll do this just for people who are having trouble with that. We factored out a 16. Pulled the 4 out. 4 was out here. And then I hope you can read that. 1 minus sine squared theta is cosine squared theta. Square root of cosine squared theta is cosine theta. That 4 I popped way out here. And then here I still have what? 4 cosine theta d theta. Okay. So what's 4 times 64 times 4? That's a constant. I can pull that out of the integral. What is that? Yeah, go ahead and get your calculator. There's no shame in that. I don't know what it is. 256? 256 integral sine cubed theta cosine squared theta d theta, right? Sine cubed cosine theta cosine squared. Right? Yeah?
No, never mind.
You got it? Now where are we? We're back to this now. Okay? So we have on the left-hand side, if the power of cosine is odd. No. Okay, second one. Power of sine is odd. Yes. What do we do if power of sine is odd? We peel off a sine squared. So I'm going to peel off a sine squared. What is it? What's wrong? You sure? You don't like this 4 cosine, do you? Okay. Are you happy with this 4 cubed 64? Yes? And this sine cubed here? This became 4 cosine theta right there. And then this was 4 cosine theta d theta. And then that 4 comes out with that 4 and everything, 256. Okay?
You brought out all the
All the constants.
Full 4s in the 64.
Yes. Uh-huh.
That's
Is that just not 256? Who said it was 256?
That was 1,000.
Okay, okay. Who said that? I let y'all do it. That's arithmetic, right? We're past arithmetic. Yeah. All right, so we're going to peel off a sine squared. Is that what it says? Okay. And sine squared theta, sine theta, cosine squared theta, d theta. Now, what's the point of peeling off a sine squared? What do I do with it? I'm going to switch what to what? The sine squared is going to be switched to 1 minus cosine squared. That's what the sheet says, right? So that's going to be 1024, 1 minus cosine squared theta, sine theta, cosine squared theta, d theta. And then the sheet even tells you what substitution you should make now. Use cosine. U is equal to cosine theta. Du is what? Negative sine theta, d theta. Do you have negative sine theta, d theta here? Well, you have. You're close, right? You're close. You've got sine theta, d theta. You're off by a sign. So you make this minus. You make that plus, right? And then it'll match up. And then I can rewrite the whole thing. So let's see what it's going to become. In terms of u, yes. So I have 1024. It's going to become what? Negative 1024 because of the negative du. And then this is going to become 1 minus u squared times sine d theta. That's part of my du, right? So just the cosine squared, which is u squared, and that du is too far out. Well, I think the other method was a little faster, don't you? But like I said, that method only worked because this problem was written the way it was. If I put the x cubed on the bottom, it wouldn't work. All right, at this point, I think we're home free now at this, right? Any questions on any of this, though?
Where'd the d theta go?
It got replaced, this right here, I'm replacing all my cosine thetas with u. So the derivative of cosine theta is sine theta d theta, well, negative.
Yeah.
Switched it. And so here's sine theta d theta. That was the du. This right here is the du.
Okay.
Well, negative du, and the negative popped out. We good? Okay, continuing. Negative 1024 integral u squared minus u to the fourth du. And then power rule. Negative 1024. I guess I can multiply it through, or I can do it separately. 1/3 u cubed minus 1/5 u to the fifth plus a c out here. Do you agree with that? All right. Let's go ahead and distribute this. Does 3 go into that? No. Doesn't?
No.
So I just leave it as negative 1024 over 3.
Neither.
U cubed minus plus 1024 over 5 u to the fifth. Plus c? Y'all still there? Okay. What was u?
Cosine theta.
Cosine theta. So our answer is negative 1024 over 3 cosine cubed theta plus 1024 over 5 cosine to the fifth theta plus c. We're not done.